question.
Are you going to be able to keep a straight face through class?
You can't tell.
Is there a quiz for me? I don't think there is. Not in this one.
All right.
No questions.
I'll let you stare at the destroyer while thinking about product rules.
How old's that outfit?
I just got it. It's like 20 bucks at Amazon. Melting. What?
Fan was to keep it inflated.
Yes. And I gotta take it off because it's like killing me. Alright, so we were talking pigeonhole principle. And I left you with an interesting question, which was any positive integer has a multiple of itself consisting of only ones and zeros. So did anybody play around with that? Either proving it or trying it in different cases?
Nobody beats your gaze.
Alright, here's what we can do. So let n be a positive integer. And let's think about things modulo n. Right, remainder when we divide by n. So what can something be congruent to modulo n?
0 to n minus 1.
0 to n minus 1. So let's make a series of buckets. We're going to make n buckets. And this is the bucket when you're congruent to 0. This is the bucket when you're congruent to 1. And we can put each number in one of these buckets based on its congruence modulo n. And we have n buckets. And now I'm going to form a set of integers. The set of integers consisting of consecutive ones up to and including the integer with n plus 1 digits. So I have n plus 1 elements in this set. I have n buckets. If I now place these numbers into these bins based on their congruence modulo n, the pigeonhole principle tells me at least one bucket will have two numbers in it. Agreed? So at least, so by pigeonhole principle, at least one bucket has two numbers. Let's call them A and B. And let's just assume that A is the smaller of the two. Well, since A and B are both congruent to the same thing, A is congruent to something modulo n, and B is congruent to the same something modulo n. That's what it means to be in the same bucket. A minus B is congruent to 0 modulo n. Or let we do B minus A, same thing.
Wait a minute, I think I know what you said.
So B minus A is a multiple of n. But what does B minus A look like if I write it out? What digits can it have in it?
Just 1, 0, 0.
Just ones and zeros. B is going to be some big long string of ones, and A is going to be some smaller string of ones. And when I subtract, I'm going to get a bunch of ones followed by a bunch of zeros. And I know that's a multiple of n because this number and this number are congruent to each other mod n, so their difference is congruent to 0 mod n. And there you go. And it's not a constructive proof. We don't know which of these numbers are congruent to each other, and so at the end of the proof, we have no idea what this number is. That's a multiple of, say, 13.
But we know it exists.
But we know it exists. And we kind of have an algorithm to find it. We take 14 of these numbers, and we find which two are congruent to each other. And we know that by the time we've gone through 14 of them, at least 2 of them will be congruent mod 13. And then we subtract them and we're done.
So in a way, it is a constructive proof.
So it is in a way that the sieve of Eratosthenes is constructive for primes. You can use it to eventually get any prime, but it's an algorithm as opposed to a formula. So that's a somewhat less obvious application of pigeonholing.
Kind of gives clues to how it could be useful, because you look at the general idea and you go, well, yeah, duh, but
Yeah.
how is this useful?
Right.
Well, that's how it's useful.
Yeah. Because that's not a way that we would normally think of packing boxes. All right, let's do one more. So if you pick n plus 1 numbers less than or equal to 2n, at least one of those numbers is going to be a multiple of one of the other numbers you picked. And for small n's, you can work this out and believe it. So for example, n equals 6. So you want to pick 7 numbers from this list. Such that no number is a multiple of another number. And clearly we can't pick 1, because everything's a multiple of 1. And if we pick 2, then we cannot pick any other even numbers. So we could pick 2, 3, 5, 7, 9, 11. That's only 6 numbers. We can't pick a 7th number. And if we pick 3, we could also pick 4 and 5 and 7. We can't do 8, we can't do 9, we could do 10 and 11. 1, 2, 3, 4, 5, 6. We only got 6 numbers.
Couldn't be 10.
It's not a multiple of 3 or 4.
It is a 5.
Oh, it is a 5, you're right. So is it possible to pick n plus 1 numbers in this range such that none is a multiple of the other? And it turns out it's not. And we can prove that with the pigeonhole principle. Well, I set up my laptop. I don't have a natural intuition myself for these kinds of proofs. And I think, like most things, if you do a lot of these, you start to develop intuition. But I'm not going to ask you really subtle pigeonhole questions on tests. I'm likely to ask you things like, you know, if 8 people are in a room, convince me that 2 of them were born on the same day of the week. Or what's the smallest number of people you can have in a room such that no 2 were born on the same day of the week? So applications like that. But nonetheless, these kinds of questions are fun to see because they're kind of startling in how they use this simple principle. So let's prove this. So pick n plus 1 numbers. And each of these is going to be bigger than or equal to 1, less than or equal to 2n.
Well, we once again use congruency, can't we?
How?
I almost have that.
Okay. I believe it. Well, let me work through this, and if you see. We want to show that none is congruent to 0 modulo another. So here's our n plus 1 numbers, and each of these is less than or equal to 2n and bigger than or equal to 1. Write each AI as 2 to some power times some integer qi, where qi is odd. In other words, divide out all the 2's. So the number 10 we would write as 2 squared times, as 2 times 5. The number 100 we'd write as, I shouldn't be doing this in my head, 2 to the 4th times 25, 2 squared times 25. Right, so divide out all the 2's until you're left with an odd number. Right, or if you like factor it into primes. Group the 2's into here, take everything else, multiply them, that's qi. So we can write each I in this way, 2 to some power times an odd number. So how many odd numbers are there that are greater than or equal to 1 and less than or equal to 2n? And you can do this by cases. So if n equals 3, we have 1, 3, 5. If n equals 4, we have 1, 3, 5, 7. If n equals 5, we have 1, 3, 5, 7, 9. And we could do an inductive proof to show that the answer to this is n.
Yeah.
So here, I have a set of n plus 1 odd numbers. And in this range, I have only n odd numbers.
So at least 2 will be.
So at least 2 of these qi must be the same. Right, so a set of ai as n plus 1, sorry, a set of qi as n plus 1 odd numbers So the set of QIs has n plus 1 odd numbers between 1 and 2n. There's only n unique odd numbers between 1 and 2n. Therefore, by the pigeonhole principle, at least 2 of the QIs are the same. And so assume QI and QJ are the two elements that are the same. Doesn't matter what I and J are. And so AI, remember, was 2 to some power times QI. AJ was 2 to some power times QJ. But since QJ is equal to QI, it's also 2 to the PJ times QI, and this is also 2 to the PI times QJ. And so if AI is the bigger of the numbers, then PI is bigger than PJ. And so 2 to the PJ divides PI, and QJ is equal to QJ, and so AJ will divide AI. And if AJ were the bigger of the numbers, then PI is less than PJ, so 2 to the PI divides 2 to the PJ, and QI divides QI, and so AI divides AJ. And so one of our numbers divides the other.
Seeing how knowing the number of odds tells us that one is a multiple of another.
If you've only got 10 odd numbers, and I'm giving you a basket with 11 odd numbers in it, you know 2 of those numbers must be the same, right?
Yeah.
That's the pigeonhole part of it. So now we know that somewhere there's 2 numbers, say QI and QJ, that are the same.
But why are we using odds?
Using what?
Odds.
Odds. Because I divided out the powers of 2 so that these are odd. And given that these are the same, so let's suppose that AI is bigger than AJ. And we can do the same argument if AI is smaller than J. If AI is bigger than AJ, then AI is equal to 2 to the PI times QI. And if AI is bigger than AJ, then this power of 2 must be bigger than this power of 2. So it's 2 to the PJ plus some extra amount times QI. Equals 2 to the PJ times 2 to the K times QI. And if I rearrange these, 2 to the K times 2 to the PJ, and QI is the same as QJ. And 2 to the PJ times QJ, that's just AJ. So with some algebra, you can show that AI is a multiple of AJ. The punchline is we write each of these as a power of 2 times an odd number. Right? So here's our first one. Let's say it's 2 squared times 3, 2 to the third times 5, 2 to the fourth times 3, 2 to the first times 7. If we have 4 numbers and we knew we only had 3 odd numbers, somewhere 2 of these are going to have to be the same. And if you have something in this form and something in this form, the bigger one's a multiple of the smaller one. Because they're just a different power of 2 multiplied by the same odd number. It's a little weird. let's move on to permutations and combinations and probability. And this is related to what we've been doing. And while we're doing that, let me find out your next homework, your next programming assignment.
Almost like this is a computer science.
Almost.
One life to left in the room.
Despite all happens in the country.
Yeah. All right, so we're going to talk about
Pascal's trying.
science behind this later. But we're working with something called Pascal's triangle. And I'll show you briefly on the board how to construct it. Your assignment is to write a C program that prints out the first 15 rows of Pascal's triangle, using the properties of Pascal's triangle, not just 15 print statements. Oh.
What, we can't just have 15 printouts? Or one really long?
Or just one really long one, yeah. So here's Pascal's triangle. Start with a 1, and write down a 1 underneath it. And think of blank spaces as zeros. So think of zeros over on the left, over on the right. For any pair of numbers, we're going to write down the sum of those numbers below them. So 1 plus 1 is 2. We think of a 0 over here, 1 plus 0 is 1. We think of a 0 over here, 1 plus 0 is 1. There's the third row. The fourth row, and this is always going to look like 0 plus 1, that's going to be a 1. 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 0 is 1. That's the fourth row. And you can keep going. So what's the fifth row look like? Well, it's right up there. Ignore that. Right, it's always going to start with a 1,
That's like 4,
and then a 4,
and a 6,
6,
4,
and a 1. All right, that's Pascal's triangle. And it's tied into probability. It's tied into binomial coefficients, expansions of a plus b to the n. It's tied into prime numbers and all kinds of weird things. And I had...
Isn't it also tied to powers of 2?
Yes. I had a student do a project once on Pascal, and he pointed out that Pascal actually looks like Squidward from SpongeBob, which I never realized before, but you can kind of see.
I don't see how.
Just the long.
Yeah, it's just the expression, I think, and the longer nose.
Yeah, he doesn't look like a happy person.
Well, neither is Squidward, that too.
Expression of completeness, students, commonality.
But he was brilliant. Squidward may be brilliant too, I don't know. All right, so that's your programming assignment, and it's due in a week. And same as before, write your code up, test it, get it to run, and then show me your source code and the output of running it in a PDF. Submit the PDF through Canvas.
2 questions.
Yeah.
How many rows we should go?
15.
So 15 is fine. I'm thinking if we can use arrays of that, arrays for that.
Yes.
And the next thing I didn't get was, I don't know how it is working, but I don't know what was those zeros over there.
Basically, you just always start with a 1 and you always end with a 1. But if you want to stick to this rule of adding the 2 numbers above you, you can think of this as kind of a 0 and a 0. And then it's exactly the same thing. 0 plus 1 is 1. 1 plus 0 is 1. And you just write each number by the sum of the things above it. And that can help with the program. Or you can just say, always put a 1 in the beginning.
Yeah.
Depends how you like to think about it.
Is that okay? To always just put 1 on the end?
Sure,
Okay.
absolutely. And you're welcome to format it just like this, just print everything from the left, as opposed to making it look like a nice triangle. But if you want to make it look like a nice triangle, that's a fun problem too. And it depends on how many digits you have. If I know ahead of time that I'm going to have a 4-digit number down here, that tells me how to space the earlier stuff. So you can pre-generate. it's a proportional font, you're good to go. You're just counting spaces. If it's not a proportional font, then it's going to be really hard.
Is the default putty font proportional?
I think so.
You
Sorry, fixed, not proportional.
Fixed width.
Yeah. The default putty font should be fixed, which will work well.
But I don't think it copies it that way. I think it copies it as plain text and then prints it out.
So we can make a really fun gardening sign where you got.
I recommend Consolas. Consolas.
Consolas or most couriers are fixed pitch. So like Courier, Tandem, New, or New Courier. Or if you know LaTeX, you can do it in LaTeX really easily. Like a LaTeX file. We haven't
No,
talked about that
I
yet.
think I'll pass on that one.
Okay. I'm gonna do that talking later.
Yes.
Yeah.
I know I could just like Google it, but that's time
Yeah, yeah.
and energy.
And one of the things Pascal's triangle does for us, right, these are the same as these. So if you want to write x plus 1 to the 5th, you just use this row, it's x to the 5th plus 5x to the 4th plus 10x cubed plus 10x squared plus 5x plus 1. You can impress your friends.
There's so many relations in that triangle.
Oh, it's freaky, man.
Brain bending.
Yeah, it does some weird things, and I don't understand a lot of them. But like if you add up across each row, that's 1, 2, 4, 8, 6, 10, 11, 15, 16. Right, so the sum across each row is a power of 2. And that's not too hard to show, maybe, if you believe each of these is the sum of the things above it. Because when you add these together, you're adding these, plus these, plus these, plus that, plus that. So you're like double adding. But
There are
there's
weird things with the diagonals.
there's weird things with the diagonals. In particular, these are your triangle numbers. 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. So that one pops out. And there's something weird with primes. If you're in a prime row, all the numbers are multiples of that prime, except for the ones. So here's row 3, and all the numbers in the middle, they're multiples of 3. Here's row 5, and all the numbers in the middle are multiples of 5. But row 4, we find a number that's not a multiple of 4.
How does that happen?
I don't know about why that one comes to be.
Great question.
Excellent exam question, no. Yeah, the other thing is, like, this is 11 to the 0, this is 11 to the 1st. 11 squared is 121, 11 cubed is 1,331. And if you handle overflows gracefully, you find that pattern repeating. So yeah, we'll have fun with Pascal's triangle, and we'll see why some of these things happen. But to get there, let's talk about combinations and permutations. And we've already been doing this with the product rule and the sum rule, but let's formalize it. So a permutation of n objects. Permutation is just an ordered arrangement of objects. So for example, when you shuffle a deck of cards and you look at the order in which those cards are, that's a permutation of that set of 52 cards.
Did they teach these in like Algebra 2 in high school?
I don't think they did when I took Algebra 2 in high school.
No.
That was a while
It's
ago.
probably changed because I vaguely remember something like this and
I wouldn't be
I
surprised.
didn't
We
get it.
talked about this in the next one.
Yeah. in 7th grade, they're talking about cancer. In science, they're doing like little exercises where they pretend that they get their life story in an envelope, and it's like how old they are and how they lived and when they died, what they died of. And yeah, I mean, it's important stuff, but it's kind of startling to me that like it's so prevalent in our society right now that it's like, you know, a 12-year-old science topic. So yeah, permutation is an ordered arrangement of objects, 52 cards, you shuffle it up. What you have is a permutation of those 52 cards. The order is important. And our permutation is an ordered arrangement of R objects. So if you take the top 5 cards off a deck of cards, and you look at them and you pay attention to their order, that's a 5 permutation of this set of 52 objects. So if we have a set of 3 objects A, B, C, then A followed by B followed by C, that's an example of a permutation. So is B followed by A followed by C, or C followed by A followed by B, and so on. Those are all permutations. A comma B, or C comma A, or B comma A. Those would be examples of 2 permutations. Ordered arrangements of 2 things. So for example, you have 5 students. And we want to pick 3 of them to stand in a line. So you're going to pick who's first in line, who's second in line, who is third in line. So we can break it into 3 tasks. Pick the person who goes first, pick the person who goes second, pick the person who goes third. The first task can be done 5 ways, the second can be done 4, and the third can be 3. That's the number of ways that we can satisfy that. So there's 5 times 4 times 3 equals 60 possible permutations. And we're going to do this a lot. So we have a shorthand.
Where does the times 4 come from?
After the first line, first student is in the line, you only
so
got.
the first student you pick, you have 5 options, and the second you pick, you have 4.
Yeah, because the first student can't be picked again, so you've only got 4 to pick from. So P parentheses n comma r means the number of r permutations of n objects. And so over here we could say the number of ways we could do this was just P 5 comma 3. 5 objects taken 3 at a time. And we have a pretty simple formula for P of NR. Any ideas how we find that?
Something with a factorial.
Say again?
Something with a factorial.
Yeah,
Probably, well, it might even be simpler than that. It might just be, what it would be? N factorial over n minus something factorial?
N factorial over R factorial?
N minus
Something like that.
Factorial.
N factorial over R minus 1 factorial.
So why?
Because that's how it is.
So how could we find this if we didn't know anything about factorials? And I just said, how many R permutations are there of n objects?
Make a grid.
Could make a grid. Let's go less fancy than that. Let's think about the product rule.
We could find all the permutations of just the whole set of 5 of n,
Mm-hmm.
and kind of.
And when we computed P of 5, 3 over here, using the product rule, right? What if I had said there were n students, and we wanted to pick R of them to stand in line? We know the number of permutations is going to be P of n comma R. And so we can't do this, but we can do something very similar to that.
We can do n times n minus 1.
Up
N
No,
minus
until,
2.
up until we reach
N minus R.
R. Yeah.
Right? Number of ways to pick the first student is n. Number of ways to pick the second student is n minus 1, n minus 2, and so on. And we want R of those. So that will go up to, see, if we wanted 2, it will go up to n minus 1. If we wanted 3, it'll go up to n minus 2. So it'll go up to n minus R minus 1.
Which then can be using factorials and factorial divided by R minus 1 factorial.
Yeah, so we can clean this up and say n times n minus 1, n minus 2, n minus R minus 1 equals so what's the next term here? N minus R. If I were to continue this sequence, right? So if I just add all this extra junk on the end here and I divide by it, I don't change the value. But this extra junk that I wrote turns this top into 1 times 2 times 3 times all the way up to n minus r plus 1, n minus r, n minus r minus 1, n minus r minus 2, and so on all the way up to n. This is just n factorial. If you do it with a number instead of n, it jumps out at you. And this is just n minus r factorial.
Is it n minus R factorial or is it n minus R minus 1 factorial? Because we were using our 5 or 3 example earlier.
So we want n minus r minus 1 in our expression here. So this goes up to and includes r, but not r plus 1, which is what this is.
Okay.
So let's try it. So let me write the punchline, n factorial over n minus r factorial. So let's try it over here. P of 5 comma 3 equals 5 factorial over 5 minus 3 is 2 factorial. That's 120 over 2. That's 60.
Oh, okay.
And if you take 5 cards off the top of a deck and you want to know how many different ways you can do that, paying attention to the order, right, that's 52 factorial over 5 factorial. And if we write that out, sorry, n minus r, 52 minus 5, 47 factorial. And if we expand these out, 52 factorial is 52 times 51 all the way down to 1. 47 factorial is 47, 46 all the way down to 1. And all of the terms in the bottom will cancel a term in the top, and we're just left with this, which is what our product rule would tell us. Number of ways to pick the first card, second, third, fourth, and fifth. So this is really just encapsulating the product rule into a nice little single formula. So if you have 10 people running a race, and you're going to give out 3 medals, one for first place, second place, and third place, how many possible combinations are there of ways that medals can be handed out? How many possibilities? 10 runners, and you've got 3 medals to hand out. And so the question is, how many ways can we pick 3 people who are going to get medals? Yeah, where the order matters, because one person's going to get the silver, one person's going to get the gold, one person's going to get the bronze. So we've got 10 objects, and we're trying to find groups of 3 of them, where we pay attention to order. That's just P10, 3, the number of 3 permutations of 10 objects, which by our formula would be 10 factorial over 3 factorial. Sorry, 7 factorial.
10 minus 3 factorial?
Yes. Cool. 720. Number of ways that you can sit 6 people at a table with 6 chairs. So 6 people, 6 chairs. So we're trying to pick permutations of 6 people out of a set of 6. And we want to know how many different ways we can order that. That's what it means to put them in seats. That's P of 6 comma 6. Which is just 6 factorial. Which before I told you all this stuff, you would have already known. Because the first person can sit in one of 6 spots, the second person can sit in one of 5 spots, and then 4, 3, 2, and 1. So this includes those cases of just combinations of n objects from a set of n.
0 factorial is just 1?
Yeah. Trust me. It makes things work. Kind of like 2 to the 0 is 1. It makes things work. But you can define factorials using something called Stirling's formula. Look up the Wikipedia page on Stirling's formula. It's fun.
Does Stirling formula have anything to do with the Stirling engine?
I don't know.
Oh, Sterling Silver.
Probably not Stirling Silver, but maybe engine. I don't know.
Yeah.
But it's a function that, among other things, when you give it an integer value, it gives you back a factorial. But it's defined for all values except negative integers. And it's got relationships with pi and all kinds of other stuff.
Stirling's approximation?
No, that's a different, that's a formula for...
It's saying Sterling.
Sorry, it's not Stirling's, it's the gamma function.
That's Actually,
we go.
this is Stirling's formula approximates
Approximates
I think that's
factorials.
fine.
Yeah, look at the gamma function. That's the fun one.
I don't know where it went. There it is.
That's a very
I can
odd
use
graph.
Yeah. All right. We are done. I will see you later. Yes. I'll leave with a graph of the gamma function on the board. We are finishing up. Here we go.
What is this?
We would have to do that back when all the
What?
I think right back when all
It could be. That would be awesome.